So let's dive into a really fascinating puzzle at the heart of modern AI. The entire field, as you know, is built on this idea of learning from massive amounts of data. But more and more, it's running headfirst into the hard wall of data privacy. The solution is an incredible field called federated learning. And it all starts with a question that sounds, well, impossible. And that right there, that's the central paradox that federated learning is trying to solve. You see, our best AI models, they're hungry. They crave vast, diverse data sets to learn from. But the most valuable data, your medical records, my financial transactions, our private messages, that data is, and absolutely should be, locked down tight. So how do you bridge that gap? How do we train a model on data it's literally forbidden to see?
Let's make this really concrete. Picture a bunch of different banks. Each one has its own little window into what financial fraud looks like. If they could just pool all of their data, all of their knowledge, they could build an almost unbeatable fraud detection system. The problem? They are legally and ethically forbidden from sharing that customer data with each other. I mean, no way. So you have this classic standoff, the quest for better security versus the non-negotiable need for privacy.
And this tension, well, it has a name, the privacy paradox. And this isn't just some theoretical problem for banks. It's a huge practical barrier in healthcare and self-driving cars, really, in any field that wants to get smarter using sensitive data. This is where collaborative intelligence slams right into our fundamental right to privacy.
The solution that emerged is, well, it's just a beautiful inversion of how we've always done machine learning. For decades, the standard playbook was collect massive amounts of data, bring it all to one powerful central server, and train a model there. Federated learning completely flips that script. It says, what if, instead of the data coming to the model goes out to the data?
Okay, so how does this cycle actually work in practice? Well, first, a central server sends out a generic starter AI model to every participant. So a copy goes to each bank in our example. Then, and this is the really critical part, each bank trains that model locally, using only its own private customer data. The data never ever leaves their secure servers. Third, instead of sending the data back, they send back only the model updates. These are just small packages of numbers, the parameters, the learnings. And finally, the central server takes all those learnings from all the banks, aggregates them to create a smarter, improved global model, and then sends that new version back out for the whole cycle to start again. And that's the whole magic of it, right? This entire process is about learning without ever looking at the raw data. The central server gets to build this incredibly powerful, globally informed model without ever seeing a single private transaction. It's a pretty profound shift. Now, the most foundational algorithm for doing this is called federated averaging, or FedAv for short. And honestly, the name tells you pretty much everything you need to know. The server gets all these model updates from the different clients and, well, it averages them together to create the new and improved global model. It sounds so wonderfully simple, doesn't it? Maybe. A little too simple. And this brings us to a huge misconception in the field. If it were really as easy as just averaging everything together, well, the problem would have been solved a long time ago. But the real world is never that neat and tidy. And it turns out that this kind of simple averaging, which works beautifully in a lab, can fail and fail spectacularly in the real world. Because, the real world is messy. The data isn't clean, or perfectly balanced, or uniform across all participants. And when you try to apply a simple, naive average to that messy reality, the model can start to drift into total chaos, producing something that's actually worse than any of the models that were trained individually.
The absolute core of this problem comes down to the difference between what we call IID and non-IID data. IID, that's identically and independently distributed, that's the dream scenario for any machine learning practitioner. It means every client's local data set is a nice, clean, representative sample of the bigger picture. But reality? Reality is non-IID. Every client's data is its own unique, skewed, and biased slice of the world. And this non-IID reality, it shows up in all sorts of sneaky ways. You have quantity skew, where maybe one power user has thousands of data points, and their updates completely drown out the signal from a more casual user. Then there's concept shift, which is a total nightmare for our banking example. The exact same financial profile might be labeled low risk by Bank A's internal rules, but high risk by Bank B's. The model is getting completely contradictory instructions for the same input. And you've got temporal skew, where one person's data is all from the holiday shopping season and another's is from the quiet summer months. The global model gets pulled in all these different directions at once. This slide just nails the intuition perfectly. Trying to naively average these conflicting updates is like taking the driving directions from someone in the US, stay on the right, and averaging them with directions from someone in the UK, stay on the left. The result isn't a car that learns to drive safely down the middle, no. The result is a car that learns to swerve directly into oncoming traffic. It becomes worse than useless. It's actively harmful.
So the real genius of modern federated learning isn't just that initial elegant idea of sending the model to the data. It's in all of the complex, robust techniques that have been developed to tame this chaos, to handle both the natural messiness of real-world data and the deliberate chaos that can be introduced by bad actors.
So let's tackle those bad actors first. In this field, this is known as a Byzantine attack. It's when a participant in the network deliberately tries to poison or sabotage the global model. They might do this with a noise attack, just adding random junk to their update, or a sign flip attack, where they literally flip the sign on their updates to try and pull the model in the exact opposite direction of where it should be going. Or, and this is the most insidious one, a lie attack, where they make very slight, very subtle changes that are incredibly hard to detect.
So how on earth do you defend against that? Well, the intuition here is actually really beautiful. Think about a choir director. If the whole choir just sounds a little bit off, it's really hard to pinpoint the problem by listening to everyone at once. A good director doesn't just average the sound, they focus. They'll listen to just the sopranos, then just the tenors, then just the basses, isolating each section to find the one or two singers who are hitting a bad note. That's the core idea.
And that's exactly the intuition behind a robust defense called LASA, which stands for Layer Adaptive Sparsified Aggregation. It has two key steps. First, sparsification. Each client only sends its most significant updates, the most important changes it learned. Think of this like each singer focusing on just their most critical notes, not every little waver. Second, and this is the clever part, layer-wise filtering. The server doesn't look at the whole model update at once. It goes layer by layer, just like the choir director goes section by section. And for each layer, it uses a statistical technique to spot any update that is a crazy outlier, either way too big or pointing in a weird direction, and it just discards it. It's finding and ignoring the off-key singer in each section of the choir.
Okay, so that helps with the malicious actors, but what about that other problem, the natural differences in data, that non-IID mess? For this, the solution is a really clever shift in what we're even trying to accomplish. Instead of trying to force one single, perfect, one-size-fits-all model onto everyone, which might just be impossible, we shift to something called personalized federated learning. The goal now is to use the whole network to build a really powerful, really smart base model. Then each individual person or bank or device can take that great starting point and just fine-tune it a tiny bit on its own local data, creating a personalized version that works perfectly for its own unique world.
All right, so this isn't just some academic theory locked away in a lab. This combination of robust aggregation and personalization is what's allowing federated learning to move out into the real world, powering applications that you probably use every single day.
A perfect example is the smart keyboard on your phone. Apple's QuickType learns how you communicate. It figures out that the way you text your friends is different from how you email your boss. It predicts more casual slang in messages and more formal language in mail. Think about that for a second. It's building a personalized language model just for you on your device without your private conversations ever being uploaded to a server. That is personalized federated learning right there in the palm of your hand.
And it's not just keyboards. This ecosystem is absolutely blowing up. Hospitals are using it to train diagnostic models on medical images without sharing sensitive patient records. Financial institutions are building those fraud detection models we talked about, finally breaking through those legal data sharing barriers. And networks of cars are sharing learnings about traffic patterns and road hazards to improve autonomous driving, all without revealing anyone's specific location history.
But for any of these ecosystems to really work, they have to answer a super practical economic question. Why would a hospital or a bank bother contributing its valuable data and its expensive computing power? What stops so-called free riders from just benefiting from the global model without ever contributing anything back? This is where game theory and economics come into play. The most promising solutions are building incentive mechanisms, often using blockchain for trust and transparency. In these systems, valuable contributions can be verified and automatically rewarded with tokens using smart contracts, creating a fair and self-sustaining economy of collaboration.
So as you can see, this field is so much more than just a simple idea. It's this rich, fascinating intersection of statistics and security and economics. So let's kind of step back for a second. What are the big ideas, the key mental models you should really walk away with from all this?
Okay, 3 crucial points. First, and this is maybe the biggest takeaway, federated learning is not just simple averaging. It's this incredibly complex dance of managing massive diversity across data and systems.
Second, building a robust system means you're fighting a war on two fronts. You have to actively defend against malicious attackers, while at the same time correcting for the natural, unavoidable drift that comes from diverse data. And third, the ultimate goal itself is changing. We're moving away from this old idea of a single, monolithic master model and moving towards creating powerful base models that can serve as a launchpad for millions of personalized AIs.
And that, of course, leaves us looking out at the horizon, at the next frontier of questions. As these systems get bigger and more complex, how do we perfectly balance the tricky trade-offs between privacy guarantees, model fairness, and the economic incentives that are needed to keep the whole thing running? And maybe the most exciting question of all, can we build hybrid systems? Can we combine the principles of federated learning with even stronger cryptographic tools, like secure multi-party computation, to create AI systems that are not only intelligent, but are provably private and trustworthy, right from the ground up? That is the challenge and the opportunity that lies ahead.